Okay, so we're very happy to have today Andrew Hendrickson from Tel Aviv University, and his title is on the screen, please.
All right, well, it's good to be here. Thanks for inviting me. Yeah, for any who came in late, yes, I did see the rockets last night outside my window. It was very scary, but I'm going to give this talk anyway. So what are we talking about today? Well, let's start with the basic idea of a branching type of problem. Let's suppose we have a unitary representation. It can always be decomposed as a direct integral of irreducible representations. Okay, so if you were to take a group G and a subgroup H, and you take pi, an irreducible representation of G, and restrict it to H, it's no longer necessarily irreducible. So the question is, what can we say about the irreducible representations in the direct integral decomposition for the restriction? Okay, but this is a very general, just a very general question or context, but I'm going to get a lot more specific. So in particular, there's just some notations here. The set of unitary representations, irreducible ones of a group is called the unitary dual, denoted G hat. The set of irreducible representations occurring in a direct integral decomposition. Direct integral decompositions are essentially unique. It's, well, I don't want to fuss about those details. Anyways, the representations in the decomposition are called the support. So then we'll take F to be a number field. So in our case, G will be a split reductive group over F, A, the Adele ring of F, and we'll denote a local field FV for a place V. Okay, are there any questions before I start? Okay, so we're looking at automorphic representations in this talk. So we're interested in representations in the support of this L2 G of A mod G of F. And we have a couple reasons that we're interested in them. First off, in the context of this restriction branching problem, we have this wonderful theorem of Burger-Sarnak, which says essentially that if you take a representation on the local level, a product of finite places, let's say, a finite product of places, and denote by this G hat S its support of this L2 G of A mod G of F, then essentially what it says is if you restrict a representation, the support of that restriction is contained in the analogous HS aught sign. So if you take a representation that's contained in this L2 G of A mod G of F, in an irreducible representation of, let's just say, a G of a p-adic group, then when you restrict it to H of that group, then its support will be in L2 of H of A mod H of F. And this is similarly true for when you do induction, normalized unitary induction of unitary representations, and also for tensor product. If you take the tensor product of two representations in this L2 space, in this L2 representation, then their support is also contained in this L2 representation. So this is a very nice theorem. One consequence of this, for example, is to say that all tempered representations are contained in the support of L2 of G of A mod G of F for any reductive group. I guess I say split reductive group in this case. And that would essentially follow from the fact that if you take H, the subgroup H to be the trivial group, and you induce trivial representation up to G, that's L2 of G, and that the support of that is all tempered representation. So this theorem is telling you that its support is contained in this L2 space. So for example, immediate corollary of this is that all tempered representations lie in this space. Any questions on this? If I'm totally losing everybody, then please say so, because I don't want to do that. Okay, so we're looking at representations in this space. First off, because when we restrict them or induce them or whatever, we stay in this space for the analogous group, change of group. And the second reason we're interested in it is because we have a good description of this space for classical groups. That is, Arthur has given us a description in terms of these A parameters, which I've described here as equivalence classes of maps from some conjectural group, which may raise some red flags for some of you, but you actually don't need the existence of this group to define these A parameters. And well, these details are not too crucial at this time anyway. You can just sort of take them as read if you're not familiar with this. So essentially the idea is that this L2 space decomposes according to some representations built out of these A parameters, which are homomorphisms from this conjectural Langlands group, and they basically have this property. If you look at the corresponding local maps that you get at each place, so this conjectural Langlands group has the property that this map, when restricted to each place, restricts to a map from LFV cross SL2, where LFV is this Whale-Dillon group. So these are the local Arthur parameters. And using the local Arthur parameters, we're able to build these local Arthur packets of finite sets of irreducible unitary representations, which are then used to build the global Arthur packets, which decompose the space. Okay, so we have a decomposition of this L2 space given by Arthur in his book into these Arthur packets. So usually I get a bunch of technical people pointing out a bunch of technical observations at this time. I want to say that I'm skipping a whole lot of details about this Arthur decomposition. So I want to talk about so we obtain the local A packets, which are used to build the global packets. And then what I'm interested in looking at for an A parameter is its restriction to this SL2 factor. So I will call this the SL2 type of a representation. Okay, so given a representation in a local A packet, so this is a representation that is used to build this L2 G of A mod G of F representation. It is associated to some A parameter. And this A parameter, when restricted to the SL2 factor, we're going to define as the SL2 type of representation. Okay, so this definition is due to Clozel, who introduced it in his paper originally. And essentially, the idea is that unramified representations, this SL2 type should be unique. Essentially, the idea is that if you have an unramified Arthur parameter, then it contains a unique unramified representation, which is contained in the L packet inside the A packet, and the L packets are all disjoint from each other, which means that no unramified representation may end up in two different A packets with different SL2 types. So the idea is that every unramified representation has a unique SL2 type. The point again is that these representations, in general, a representation could be found in many A packets, but these representations are only found in packets associated to a single Arthur parameter. Okay, so why do I care about this SL2 type? It's because Clozel observed that when you, with the Burger-Sarnak theorem, you can prove that if you start with an unramified irreducible representation of some particular SL2 type, and you want to restrict that representation to the subgroup H, then again, Burger-Sarnak tells you that its restriction, the spectrum of that restriction is contained in this L2 H of A mod H of F representation. So everything in the spectrum of the restriction also has SL2 types. What Clozel was able to show is that there is a unique common SL2 type among everything in the restriction of pi to h. So pi has SL2 type lambda. There exists a unique type R of lambda such that pi restricted to h, every representation in the support of pi restricted to h has type R of lambda. It doesn't necessarily mean that that's the only type those representations have, although unramified representations in that support have a unique type, so it will have R of lambda as that unique type. And moreover, this unique type R of lambda depends only on lambda. So if I take another representation with the type lambda, then I know that also its restriction, the support, has R of lambda among the SL2 types in its support. So this map, this gives me basically a map from SL2 types of G to SL2 types of H given by restriction, or going with induction and tensor product, I get by induction a map going the other way, and tensor product I get this binary operation on the set of SL2 types. And so the idea is that this map should be the same for every representation with a particular type at any place, anytime, which is quite a powerful statement. If you think about it, that means that if, p-adic and complex and real valued, real group representations, they all have the same SL2 type map. It's very nice. Any questions on this definition so far? You all are very quiet. I don't know whether to be concerned.
It's all good.
All good. Okay, so, well, I will skip the proof of this just in the interest of time, I guess. Let's just jump to the GLN case. Let's bring things down to earth a little bit and look at this example. So this GLN case was first solved by Venkatesh in 2005. So in this case, when G is GLN, the Langland's dual group of G is GLNC. So an SL2 type is an algebraic homomorphism from SL2 to GLN, which is just an n-dimensional representation of SL2C, which by Jacobson-Morozov is in bijection with the sets of partitions of n, depending on where you send a unipotent element. Okay, so for GLN, the point is that SL2 types are in one-to-one correspondence with partitions of n. For example, the trivial representation has an SL2 type associated to just the trivial partition n, while tempered representations have a type which is just all ones, just n ones added together. Other representations go between. I'll describe in general how to construct a representation of a particular, of a given type shortly. So this means that if we want to describe explicitly this map of SL2 types given by the restriction map, so SL2 types of GLN given by partitions of n mapping to SL2 types of GLM given by partitions of m by restriction, if we want to explicate this map, then we need to, well, come up with some notation first off for partitions. And so let me state some notation first. Given a finite sequence of numbers whose positive entries sum to a value less than or equal to n, we're going to form a partition out of these numbers by throwing away anything that's not positive and then adding enough ones for the remaining numbers to sum to 1. So for example, I've written an example here. If I told you the numbers -3, 0, 3, 5, and I put them in these angle brackets, I mean by that the partition of 11, 1, 1, 1, 3, 5. Okay, so and then given a partition, if I were to just write it as xi, kind of like a sequence, then I could write xi minus a to indicate that I want to form a partition by subtracting a from every element in the partition given, and then forming a new partition according to this rule, throwing away non-positive entries and concatenating enough ones. Now, given that notation, here is the result of Venkatesh in the restriction case. So, given a representation of an Arthur type representation, and I suppose I should have said by Arthur type, I just mean it is contained in this L2 G of A, G of F representation. It's a local representation, in a local Arthur packet. So given a representation of any arbitrary type lambda I, its restriction to GLM has type given here, lambda I minus n minus m. So the idea is you should take the partition associated to GLN, this partition of n, and subtract the difference between n and m. So for example, if you're restricting from GL22 to GL19, this formula says take your partition, that is your SL2 type for GL22, subtract 3 from everything, and then form a partition of 19 according to the rule. So I have here the example 1669. If I restrict it to GL19, this would produce after subtraction minus 2336, and then after throwing away the minus 2 and adding enough ones to add to 19, I get this long partition here. So, of course, the trivial representation of type n, according to this rule, restricts to the trivial representation. That's no surprise. One interesting feature of this map is that if I were to take, for example, this GL22 representation and restrict it to GL14 or lower, then I would be subtracting at least 8 from every number in the partition, so I would end up with all ones in the partition. What this is essentially telling us is that given a GL22 representation of this type, I need to restrict it to GL14 before it is tempered, and that any 14 or lower, that restriction is always tempered. Okay. So this is quite a nice result, although I should be careful because technically knowing something is type 111 is not the same as knowing it's tempered. Although tempered things are known to be Arthur type and of type 111, I guess it's the Ramanujan conjecture that the converse is true, that everything of type all ones is tempered. So really we actually have some, only some approximate knowledge that it's tempered, I guess. And then my second example here is given any non-trivial type representation, so any non-one-dimensional representation of GLN, if you restrict it far enough, it will eventually be tempered. So it's just saying the same thing in general. So that's the restriction case for GLN. The induction case, how do I stop doing this? Induction case is kind of similar. So suppose that we want to induce from a Levy subgroup. Let's just take my example here, GLA cross GLB. Then the idea is you should look at which one is bigger, and well, it's quite degenerate. You're left with very little in the end. Well, this is in the case in my example here where you start with something that's of trivial type. So this would be a representation of type A on GLA, B on GLB, and if A is bigger than B, then this induction has this type B minus A. By the way, by this induction GLA cross GLB to GLA plus B, I mean going directly, not parabolic induction. Okay, so this is direct unitary induction from this Levy subgroup. So the formula in the theorem tells you how to do it for a more general Levy subgroup. And once again, I make this observation that if you have a representation of any type and you induce it high enough, the representation will be tempered. Sorry, just got distracted by the chat there. And then the final case the tensor product case. Given two representations of GLN, the way you figure out the SL2 product for their tensor product is to, well, I'm sorry, I'm trying to clear the annotation marks here. Your own drawings, okay. Sorry, given two representations of arbitrary SL2 type, the way you figure out the SL2 type of their tensor product is you just take any numbers from either one, add them together, and then subtract n. So, you know, if you had 1, 2, 3 on one side and you know, I guess 2, 2, 2 on the other side, you would look at 2 plus 2 minus, the order of the group is 6 in this case, and then 3 plus 2 minus 6, and so on. For example, of course, you can verify tensoring with the trivial type, produces the same type. If you tensor with a tempered representation, you get the tempered type. And the third example here is just to say that if the largest numbers in your SL2 type partitions for your two representations aren't big enough, they don't sum to n, then their tensor product will end up tempered. So I guess the moral of the story for these formulas is stuff gets tempered quickly. Anyway, so that's the GLN case. How did Venkatesh prove that? Well, in order to show that this formula holds for all representations of a particular type at any field, we only need to check it for one representation. Because remember that the map of SL2 types is the same for every representation of a particular type of any at any place. So pick the place you like. Venkatesh likes complex numbers, and he constructs a representation of any SL2 type in the way I'll describe, and then he just computes the map on that one representation to figure out the entire SL2 map. Okay, so how does he construct a map of an arbitrary type? Well, we just use parabolic induction. So given a partition of n, lambda 1 through lambda k, we can take the corresponding Levy subgroup, GL lambda 1 through, times up to GL lambda k, and then do parabolic induction from a one-dimensional character. This will be of this type, lambda 1 through lambda k. So notice that there's a difference here. I'm doing parabolic induction to do this rather than induction from the Levy subgroup directly. Parabolic induction basically says, take the partition on the Levy subgroup. Okay, that's the partition on the whole thing now. Whereas going directly from the Levy subgroup is far more of a degenerate induction because it's more distance to go. So he constructs this induced representation, and then he proceeds by induction on n, and essentially does the restriction case, restriction of an induced representation by Mackey theory. And oh no, I'm already basically out of time. No, wait, it's we started at 4:30. Started at 4:30. We're good. Have 5:30. Okay. So yeah, so the way he computes the restriction of this representation is just using Mackey theory, decomposition into double cosets. Same thing for tensor product. He takes tensor product of two induced representations. So his analysis is fairly easy. His induction case, inducing from the Levy subgroup, the way he solves that is by inducing through the parabolic subgroups. So the parabolic subgroups for GLN have an abelian unipotent radical, and so he is able to essentially reduce that case to harmonic analysis on this abelian unipotent radical in a nice way. So his paper is fairly short, just a few pages long, and he's able to solve that for GLN. Any questions before I move on to the classical group case?
Yes, so just to verify, this induction is parabolic induction or directly from the Levy? This one, induced, pi equals induced?
This is parabolic induction on this page, yes. So the purpose of this is to construct a representation of an arbitrary type so that we may compute the restriction map or whatever map using this.
And pi is like reducible, right? It can be reducible.
it is almost always irreducible. So, you know, you can just pick your chi1 through chi n to be so that it's irreducible. Okay, so that is the GLN case. Let's look at the classical group case. It's significantly more complicated. We'll consider only split groups. That's really just a convenience. It can be dropped, but well, let's just do it for easiness, and I'll just gloss over that point. So let's consider O2n, sp2n, or SO2n plus 1. So in this case, the Langland's dual group of SO2n plus 1 is sp2n, and sp2n dual group is SO2n plus 1, and then O2n is dual to itself. Oh, also I'm going to use O2n instead of SO2n because the formula is slightly, it happens to be slightly nicer in the O2n case. If we have time at the end, you can ask me why. Okay, so based on this, we once again have a correlation between partitions and SL2 types, except that because the dual group is, a classical group, there's some restriction on the partition. So an SL2 type for sp2n, for example, is a partition of 2n plus 1, where even numbers have even multiplicity. So if you have a 2, there must be 2 2s, 4 2s, whatever. And you see the rules there. I'm actually not going to do the odd orthogonal groups either, basically just to save time. So we're just going to look at sp2n and O2n. So I take an unramified representation. I should say that in the classical group case, it's necessary to take unramified representations as your candidate representation because it has a unique SL2 type. In Venkatesh's case, for GLN, everything has a unique SL2 type, so he didn't need any of that. So that's one minor complication in my case. So suppose you have an unramified representation, then I give you the restriction map here. It says take the partition and subtract the difference between the groups. Okay, it's the same. It's the same as the GLN case for restriction. I have this epsilon in the preamble. That's for the next case. So that's very nice. Let's look at induction. So if I induce from a subgroup, let's say sp2a cross sp2b to sp2a plus 2b, it says that you should figure out which is bigger, A or B, and subtract the smaller one, 2A in this case. Except, there's an exceptional case. The exceptional case is where you're inducing something of a trivial type from sp2a cross sp2b to sp2a plus 2b in particular. And what happens is, instead of, in the end, instead of filling in your partitions with 1s, you fill them in with 2s, which is a really curious exception. I will explain why that is in a bit, but essentially this is the same formula for GLN, except for an exceptional case. Let's take a look at tensor product. If you just look at the top bit, then it looks very similar. Again, to figure out the SL2 type for tensor, you would add any two arbitrary numbers and their types and then subtract 2n plus epsilon. 2n plus epsilon, I guess 2n minus epsilon, you factor out the minus, is the trivial type for that group. So sp2n, the trivial type is 2n plus 1. O2n, the trivial type is 2n minus 1, comma 1, because it has to add to 2n. Anyway, you see that in this tensor product case, however, there is a very complicated exceptional case as well, which I don't really expect you to read all of, but essentially there's a lot of 2s showing up again in the end. So let me just talk about these cases for a minute. So as I've already said, they're very similar to GLN. So, sorry, just a moment. My wife's telling me Hamas is going to launch rockets at 6, so I better be done on time. So, sorry. So I've already noted that there's very similarities, but that we have some weird exceptional cases. But first, before I explain why that is, you can check from the formulas I've given that it respects the rules of partitions, regarding multiplicity of even numbers, that restricting the trivial representation is trivial, and so on. All of these observations that you would expect. Tensoring with tempered is tempered, and so on. So I want to explain why some exceptional cases pop up. And for that, I want to look at the mixing cases. So in addition to just solving restriction from sp2n to sp2m and so on, I also did between sp2n and gln and induction going up and down and so on. I had to because of the inductive structure of this proof. So when I did that, I encountered this curiosity that if you take the induction from O2n to GL2n, it's always tempered. Either you take the trivial representation and you get this variety, L2, GL2n, mod O2n, or any unitary representation, it's always trivial, tempered, when you induce from O2n to GL2n. This is because this variety is what's called a strongly tempered spherical variety. I don't want to get into it. But if you look at sp2n, if you take a non-trivial type representation, then inducing sp2n to GL2n is, once again, type 1, the tempered type. I can't say it's tempered for sure, but conjecturally tempered. But then the curious exception happens if you take the trivial representation of sp2n, or one-dimensional character, I guess, and you induce to GL2n, you don't get tempered. Instead, it's of type all 2s, which is sort of a surprising exception. So in the base case, for example, sp2 is the same as sl2. So you're looking at inducing from sl2 to gl2, which is just one dimension difference. So it's supported on one-dimensional representations, which have the trivial type. So that's type 2, right? So that's the base case. It's just a 2, and every other case kind of reduces to this. So essentially, what I've come to realize is that the symplectic group is a little bigger than the orthogonal group. It's just a little bigger to GLN. And so O2n is very far away. So when you induce up, you get something tempered. sp2n being a little closer is not quite tempered when you do the induction. It's curious. And so because this whole proof, every case reduces down to other cases, all of these 2s start popping up in the other cases as well, based on this. It's quite interesting. It even propagates into the orthogonal group cases, even though this is from the symplectic group, because my proof uses theta correspondence to reduce the orthogonal cases to the symplectic cases. So it's quite interesting. Any questions on this point? Sorry about this. So I'd like to talk about the proof in the classical group case. It's more complicated. The first problem is that we can't form a representation of an arbitrary type in the same way that Venkatesh did by parabolically inducing from a one-dimensional character on a Levy subgroup. A Levy subgroup for example, sp2n looks like, let's just take a maximal one. It looks like there's a GLN part, say GLA, and there's a sp2n minus 2a part. So there's a GLN part and a sp part. And essentially, if you were to parabolically induce a representation like a one-dimensional representation, in fact, we can even do better than that. Let's take an arbitrary SL2 type for G, and we'll, thinking of it as a partition, some of the numbers in the partition are repeated. So let's take out all repeating numbers and write it as tau. And then, so I'm going to write the SL2 type lambda here. I really should be annotating this. Lambda as tau plus tau, where tau is just 2 copies of any repeating numbers, and then the lambda prime is a partition of a smaller number made up of distinct odd numbers. Odd numbers because even numbers have to have even multiplicity, so any even numbers will definitely end up in the tau part. Now suppose I take an GLM representation of type tau, and rho a representation of this SL2n factor of type lambda prime. Then this parabolic induction does yield the type lambda in the end. Okay, so if I want to produce a representation of a particular type lambda, I can get part of the way with parabolic induction by factoring out the even multiplicity elements and putting those as the type of a GLN representation of the Levy subgroup. And any distinct odd numbers remaining, I'll construct a representation on an SP symplectic subgroup and then parabolically induce from there. If I can do that, then I can form a representation of any arbitrary type by parabolic induction. But the issue is this representation rho, which has a type of distinct odd numbers only. This rho is it's I guess a unipotent representation. It's not, you can't express it via parabolic induction. Instead, I construct it via the theta correspondence. So let me see how I do that. Sorry, let me clear this. To form this representation rho with distinct odd numbers in this type, I use iterated theta lifting. We start with a one-dimensional character of a smaller group. So let's say that we want to find a representation of type 359 of the group. I guess that would be SP16 because it's a partition of 17. So the way I would do it is I would start with an unramified character, let's say trivial representation of SP2. As an SP2 representation, the type is 3. And then I can theta lift that to 08. Okay, so an SP2 has a partition, an SP2, the trivial representation has a type of 3. Its theta lift to 08, the type will be 3, 5. Remember that for 08, the partition has to add up to 8. And then by lifting up from 08 to SP16, I obtain 359 as the partition. Okay, so this relies on a number of facts. First off, this unramified theta correspondence is known by Clozel and Rallis. We know exactly that the theta lift of an Arthur type representation is still Arthur type. We know exactly the SL2 type that it'll be. And basically the way it works is if you go from a symplectic group from an orthogonal group, like I've done here, SP2 to 08, the number you should concatenate to the type is 1 less than the difference. And if you go from orthogonal to symplectic, you would concatenate 1 more than the difference. So 8 minus 2 is 6. I add a 5 because it's SP2 to 08. 16 minus 8 is 8, but I add a 9 because it's going orthogonal to symplectic. This once again kind of reflects the idea that symplectic group is a little bigger than the orthogonal group. So anyway, by doing iterated theta lifting in this way, I can build a representation of type any list of distinct odd numbers. And this, I'll have no problem with the theta lift being non-zero or any problems like that, as long as I go in increasing order of the numbers of the partition. So it all works out in this way. Okay, so I can form a candidate representation of a particular type then by doing this iterated theta lifting to obtain this unipotent representation. Sorry, again, my family's all calling me about the rockets. I really need to try and force quit Skype somehow. I'm sorry, everyone. Okay, I think that did it. By forming this unipotent representation and then doing parabolic induction, I get a representation of any arbitrary type. Yes, sorry. So therefore, I obtain a two-part structure for the proof. I do the restriction argument, for example, of the induced representation in the same way as Venkatesh. I do Mackey theory, double coset decomposition. But then for the unipotent case, when I reduce it down by induction to the case of restriction of a unipotent representation, I need to use theta correspondence. And that's where things start jumping between symplectic and orthogonal groups. Now let me say, I would have preferred to only solve the SP2N case, but because of this theta correspondence use, I had to solve the even orthogonal case. If you wanted to solve the odd orthogonal case, you would have to do theta correspondence with the metaplectic group instead. So that's how you would solve that case. And then the other difficulty with this compared to Venkatesh's proof is when Venkatesh did GL2A cross GL2B to GL2A plus GL2B, that was going from a Levy subgroup. But in this case, SP2A cross SP2B is not a Levy subgroup. It's a maximal spherical subgroup. So you can't induce through some intermediate group and do harmonic analysis in that way or reduce it to a case of parabolic induction. Instead, the only way that we can understand this is to essentially consider it as a spherical variety and do the, Saccaritis Venkatesh boundary degeneration stuff on it, some harmonic analysis to try and solve that case. Except that in their book, Saccaritis and Venkatesh only considered the L2 space of the spherical variety itself, whereas in this case, we're taking an arbitrary unitary representation, or an Arthur-type unitary representation at least, of SP2A cross SP2B and inducing it. So it's an object that's a little more complicated because it's induced from a unitary representation rather than L2 of the spherical variety, which would be inducing from the trivial representation. Okay, so that becomes quite complicated. But I just wanted to mention some applications of this. If you know the SL2 type of a representation, then you can figure out an LP bound for its matrix coefficient decay, a very good one. I describe how to do that in my thesis using the exponents of the representation. Essentially, Moglin showed that how to do this first. I just sort of translated what she did. And I'm also hoping to extend this boundary degeneration stuff to actually obtain a Plancherel decomposition for these spherical subgroup induced representations rather than a simple statement about SL2 types. So I essentially, I'm not done with this part yet. So this is essentially all I wanted to say at this point. I guess I'm actually a little early, but I can just have time for questions. So I hope my pacing was okay. I'm not too excited to do.
Okay, thank you very much. Now it's time for questions.
Yes.
So I have a question. I mean, you mentioned the metaplectic group a little, and there's a whole bunch of natural questions that probably go back to Clozel's corollary, even and understanding what those representations are. Have you worked on that? What can you tell us about that?
What do you mean understanding what those representations are?
Well, I mean, is Clozel? So, for example, I could take SP2N and restrict to GLN. So the metaplectic double cover of SP2N and restrict to the GLN that embeds, for example. And so are there similar theorems?
I did compute the SP2N to GLN restriction case. I didn't show it on these slides, but I did compute that case. So essentially, my argument would tell you some of the support of that representation.
Great.
But I don't necessarily know exactly what representations lie in that support. It's sort of a crude knowledge that you get about these SL2 types. I don't even necessarily know exactly what Arthur packet they're in, just the SL2 type.
Okay, thanks.
What about restriction to, a standard Levy of SP? That would involve GLN and SP.
Yes, so I compute that as well. Of course, if you already know how to restrict to SP2A cross SP2B, then you can restrict to GLA cross SP2B by going through that subgroup. That reduces the problem just down to the Ziegel-Levy, let's say SP2N to GLN case. And yes, I did describe that case as well. It's got sort of an interesting formula. If I can pull it up real quick. But it's similar in style to the other formulas. You're going to subtract something from the partition, and it's going to be sort of the difference in the orders between them, except, you know, it's sort of weird because it's mixing between GLN and so on. This was like my actual thesis. So I believe that case is right here, number 3. So it says you should, yes, essentially subtract the difference between the trivial types of those representations with one exceptional case. The exceptional case is when you're restricting from O2N to GLN, in which case you end up with the 2's coming in there. So, and you can see I have other cases in here as well. Not sure how to get back.
So, yeah, for the classical groups, you just talk about an ramified case, but I assume that in theory you would want to incorporate all the
Okay, so yes, so the theorem covers them as well. So only unramified representations, well, I shouldn't say only unramified, but unramified representations have unique SL2 types, whereas other representations may not. Now, let's suppose that you took a representation of type, so let me go back to this lambda R lambda notation. Let's suppose that you took a representation of type lambda, and it just has that among its types. Then I can say that its restriction has the same R lambda among its types as well. Okay? So I know that my starting point is, given an unramified representation of type lambda, all of the representations in the support of its restrictions, all of the unramified ones, have R lambda as their type. Now, to go one step beyond that would be to say all of the representations in the support, not just the unramified ones, have R lambda as an SL2 type, not necessarily the only type. And then I can go, again, a step further than that. If I started with a representation which is not even unramified of type lambda, everything in its direct integral of this restriction has R lambda. So yes, that's what you can say about that case.
Any more questions? Okay, so let's take the speaker again. So next week we have, I think, Nadav Gopel speaking. I don't know about the rest. Anyways, that's for next week. So I hope we have a quiet evening here in Israel, and wherever you are, you have a good day, and we'll see you
luck sheltering
next
from
time.
the rocket.
Pardon?
I say, wish me luck sheltering from the rockets.
Well, maybe you will be lucky and there will be no even better, but okay, let's hope for a safe afternoon. The rest. Okay. Okay, thanks again. Bye-bye.
Thank you. Bye-bye.
Bye.